hopefully my microphone is working here. So does anybody have a place they would like to start on this thing? A number, or one of the questions from the review that they would like to start on? Nobody? Okay. Well, in that case, let's start on number 2. This is a good example. Okay, so here we're talking about pumps in a system. So the system contains 2 identical pumps, and we're going to have them in operation for a certain amount of time, 1 month. And from previous studies, we know that we know a little bit about how these 2 things will perform, right? So at least one pump will fail in 7% of all 1 month's operational periods, and both pumps will fail just 1% of the time. So this is part A, I believe. So what is the probability that a single pump will fail in the coming month? Okay, so before we get there, maybe let's try to think about, I think a good strategy for these probability questions is to think about what information have they given me, and then what am I trying to figure out, and how can I get there? So we're given 2 numbers, 7% and 1%. And yeah, let's set up some notation here. Again, you can use whatever you want. Let's let A equal the event that the first pump fails. And let's let B be the event that the second pump fails. Okay. So let's try to figure out what information they've given us here. So at 7% of the time we know that at least one pump fails. So how can I represent that, or what's involving A and B, what's that the probability of? So 0.7 equals the probability that at least one pump fails. How can I write that in terms of A and B? A union B. That sounds that is correct. But I want to make sure everyone gets that. So why is that the probability of A or B?
At least one.
Mm-hmm.
Maybe both too.
Yeah. So at least one means that either just one pump fails, so either A or B fails, but you could also have the case that we're also could include the case that they both fail. So I think I'm quickly running out of space here. I think the best way to think about this is a Venn diagram. So let's let A and B be here, and we're looking at the probability that they fail. So what shaded in area on that Venn diagram represents that at least one of them fails? Is this immediately obvious to everybody? Yeah. Yeah, right. So it's this whole thing right here. And again, so we know we've seen that before. That's just A union B. So 0.7 over here is the probability of A union B. Is that okay with everybody? If it's not, speak up. This is what we're here for. Okay. So that's 0.07. So what about 0.01? What's that the probability of? That's the probability that they both fail. So in terms of A and B, how could I say that? Vanessa? Yeah. So this is a little more straightforward, I think. It's the probability of A intersect B. So the probability that the first pump fails and the second pump fails. Okay. So where now that we kind of have our information that they've given us written out there, what's the strategy here? Anybody have any ideas?
Use subtractions.
Subtraction?
Yeah.
What do you mean by that?
Usually like subtract an A intersect B out of A union B.
So why would you do that?
Because in the Venn diagram we just saw, was the case that a single pump will fail with in the like two circles.
Yeah.
Section.
Yeah. Right, so I erased the Venn diagram, but we're still there. The probability that one pump fails is going to be like this kind of a thing, right? Just that circle. That is exactly right. So how could we get there? So you said probability of A.
Probability A union B minus probability A intersect B.
Mm-hmm. So that's, but I'm still including something else there, right? So I'm still including, so A union B is this whole thing, right? And you just told me to subtract off that little piece right there.
So you have to subtract A intersect B twice.
Have to subtract A intersect B twice. So we'll subtract this thing again. That'll still, well, that's kind of, it's hard to say what that would give us, because we don't know. What we really want to subtract is this piece over here. Well, so maybe sort of conceptually, or does anybody have any other ideas? So that's almost there. That's getting very close. If you want to put that curtain, someone put the curtain down there. It's really bright. Looks like. So what am I trying to find in terms of A and B? Curtain doesn't work, huh? Well, thank you for trying. Yeah, Andrew.
Just the probability of A.
Right. So what I'm looking for is, for example, the probability of. I want to know the probability that one of the pumps fails. So how does the probability of A relate to the probability of B? So the probability that the first pump fails, they're equal. So why are they equal? You're right. Yeah. So they're identical pumps, right? So we're told here we have two identical pumps, so the probability of them being operational is the same, or operating or not, or failing is the same. So that's so we're trying to solve for one of those things, but they're equal. So any thoughts on where we can go from here? Yeah.
Are they independent? Because then you could divide the square.
So are they independent? Have we been told that they're independent?
No.
Yeah. So unless it says that they're independent, you don't want to assume that that's the case. This is a tricky problem.
So since we have the union and intersection, can we use this proposition 4 here with the union and intersection just have to
Absolutely.
achieve
Yeah. So what's that called? That's the
a
general addition rule. Absolutely. So what does that tell me?
P of A union B is equal to P of A
P of A
plus P of B minus P of A intersect B.
Exactly right. So that's our general addition rule there.
Since they're equal, we just have to
And
P of A.
exactly right. So since the probability of A is equal to the probability of B, we can now solve this thing for that. So we know the probability of A or B is 0.7. Those things are the same thing. So 2 times the probability of A minus the probability of A intersect B, which is 0.01. And now it's pretty straightforward. So now we can see that the probability that a single pump fails is 0.04. Is that okay with everybody? How we jump there? So again, I think a good strategy on these probability questions like this is try to figure out what information they've given me. If notation helps, great. If not, that's fine too. Yeah. So try to figure out the information that you've been given, and then also try to figure out what you're trying to solve for, and then start thinking about what identities, what rules do I have that can help me figure that out. So here we use the general addition rule. There's 2 or 3 other sort of general rules that we've seen, and those are kind of good places to start if we're to reason these things out. So if we want the probability of A and B, so the probabilities are the same. So again, maybe it's kind of hard to see, but we just what we did was we took the probability of A or B. Again, we added on this part, so now you could think I have the football shape there twice, and so now you could think I'm sort of separating them apart and dividing that in half, and that'll give me each piece there. So maybe that's kind of what you were trying to say, and I butchered it. So if that's what you were thinking, then that was right too. Is that okay with everybody? All right. Moving on here. So same problem. So now if one pump fails, is the other pump more or less likely to fail? And we want to support our answer with probability. So kind of ignoring the comparison for a minute, let's try to figure out what this probability is. So if I want, so what probability would help me calculate this thing? If I'm assuming one pump fails and I want to know how, if the other pump fails. Yeah.
Probability of B given A.
Yeah, there you go. So I want to know the probability that, let's say, the second pump fails, given that the first pump failed. And then I want to know if that's more or less. So I want to know how does this compare to just the probability that that a single pump fails. So is it greater than? Is it less than? Is it equal to? So what's so if we want to, so we know what the probability of B is. That's 0.04. How about this conditional probability? How do I calculate this thing? What's my general rule for a conditional probability?
Probability of B intersect A divided by probability of A.
Exactly right. So the probability of A intersect B, or vice versa, if you like that, divided by the probability of A. Exactly right. So that's another good thing to have on your formula sheet and or to memorize. Okay, so we know what probability of A intersect B is. That's 0.01. And we know what the probability of A is. That's 0.04. So that conditional probability is 0.25. So if the first pump fails, is the other pump more or less likely to fail? More likely to fail, right? Because there's not knowing anything about the first pump, the second pump fails 4% of the time. But if we know that the first pump failed, then it's more likely that the other pump failed as well there. So more would be the correct word here, and we should put in this is greater than just the probability of B. Yeah.
Just in general, like, how's the pacing of the test going to be? Like how many questions are we going to have, or like,
Mm-hmm.
that kind of stuff?
So the test will be it will be all written questions. So there's no like true or false, multiple choice, nothing like that. And then there will be between 3 and 5 questions on the exam.
Will it be made to like take your time on it, or will it be made to kind of like get through it, I guess?
Yeah, I mean that's a good question. I think you should be able to do it within the 55-minute period. Of course, that's different for every student, but I think it should be doable within the class time.
Okay.
Yeah. And I would say that this problem is probably a little bit more tricky than what you could expect to see on the exam. So, yeah, this is on the trickier end of things than what I would probably put on an exam.
Okay.
So yeah, it's hard. I mean, obviously, people take different amounts of time on the test, but I think it should be manageable within the 1 hour.
Okay.
Okay, so for the newcomers, we're just working through these exam review questions. Does anybody have one that they would like us to work through? If not, I will continue picking my favorite ones. Yeah, Kevin.
Did you go over 1 already?
No, I did not.
Can you please go over 1C?
1C, definitely. This is part C, I believe. So maybe before we do 1C, let's jump back to part A. So if I'm looking at a baseball team and I'm trying to figure out how many different rosters I can have there. So how many ways can I select 9 players for the starting lineup? So this is obviously, I'm figuring out a number of ways that I can get something. And so the question you always have to ask yourself is, do I care about the order of these things, or do I not care about the order? So you guys are on my roster. I have 18 of you in here, and I want to choose 9 of you to be on the starting roster or something like that. Does it matter which order I pick you in? Yes or no? No, it doesn't matter which order I pick you in, right? If I choose, one order, another order is the same thing as long as it's the same 9 people. So here, order does not matter. So what do I want to do? How do I want to calculate this thing? Yeah, Matt.
18 choose 9.
18 choose 9, right? So I have 18 people. I want to choose 9 of them. I don't care what order that is. That's a combination, again, of 18 things. I'm choosing 9. And again, you know what your formula is. That's 18 factorial divided by 9 factorial times 18 minus 9 factorial. And that is 48,620. Yes, sir.
Can we just leave the factorial on the exam?
Absolutely, yeah, and you're welcome even just to leave it in that form. That's totally fine. Out of time-wise, yeah, it could be easier just to leave it that way. That's totally fine. Okay, so those are my total possible lineups here that I have for this baseball team. So that's all the possible combinations of those 18 people. So maybe we'll just quickly say about Part B here. How many ways are there to select 9 players for the starting batting order? Well, so we already did one where the order didn't matter. So what are we going to do here? If I'm talking about a batting lineup or a batting order, does order matter? Now it does matter. So the person that I picked to bat first, again, that's the position in that I choose them in matters. So what's the answer going to be here? So this is a permutation, right? I have 18 things and I want to choose 9 of them, but the order does matter. So that's capital P there. So you guys remember what this is? Yeah.
Just 18 factorial divided by 18 minus 9.
Exactly right. So 18 factorial divided by 9 factorial. So anyway, that's going to be a big number. I didn't actually calculate that one out, but you could do that if you wanted to. And again, maybe just to think about this. So I have, if you think about, I have 9 positions here. 4, 5, 6, 7, 8, 9. For the first position, I have 18 possibilities. For the second position, now I only have 17 people left that I can choose from, and so on all the way down to 9. So you're multiplying all those numbers together is kind of the intuition there. Okay, so now suppose that of these 18 players, I have certain positions. So 3 of them are pitchers, 6 are outfielders, and 9 are infielders. I want to know the probability of selecting a valid starting lineup from all of the total possible ways, all the total possible lineups that I had in part A. And a valid roster contains of a pitcher, let's just say a pitcher, 5 infielders, and three outfielders. So the probability of a valid lineup in general, that'll always be the number of valid lineups divided by the total number of lineups. Is that okay with everybody? So if I know the probability of getting a valid lineup, I just need to figure out how many valid lineups there are. Okay, well, we already know the denominator. That's 18 choose 9. Anybody have any intuition for how to figure out how many valid lineups there are?
Break it down for each position.
Break it down for each position, exactly. So how do I do that?
Well, pitcher, it's 18 choose 1. Infielders, we choose 5. And then outfielders are 18 choose 3.
Okay, so you said 18 choose 1, 18 choose 3, and 18 choose 5. Okay, does that anybody have a problem with that? So it's very, very close, but
You have 18 left though when you're going down the positions. Don't you have less people?
yeah. So like here's my pitcher.
So now you have 7.
Here's my I need 3 outfielders, and I need 5 infielders. So I don't have 18 pitchers, right?
Yeah.
I can't choose from 18. I only have 3 pitchers. Yeah, so I have 3 pitchers, and I want to choose one of those pitchers. I don't care which one, so that's why it's a combination. So 3 pitchers, I just want to choose one of them. I need to choose 3 outfielders, but I only have how many outfielders? Right, so of those 6 outfielders, I want to choose 3 of them, so that's 6 choose 3. And then in my infielders, I need 5 of them out of the total number of infielders that I have. Yeah, so that's 9 choose 5. Yeah.
If there was a player that could play both positions, would you just add him into each thing?
Yeah, right. So it's like that homework question. So if there was a player that could play both things, if you had an infielder or outfielder, then it gets a little more complicated because you'd have to consider the cases in which they are. So let's say they can play both infield and outfield. You'd first want to consider the cases where they're an outfielder,
Okay.
and you want to add in all the cases where they're an infielder. So you'd sort of do 2 of these calculations and then add those together.
Okay.
Yeah. So this is, if you want to actually calculate this out, it's 7560 over the total was 48, 620, or about 15.5%. Is that okay, Kevin?
So, why, if you were to not break it up by position, how would you do that?
If you were to not break it up by position,
Or is that not even how to approach it?
yeah. So we want to break it up by position because I only have certain numbers of each type, right? So I'm going to have 9 people on my roster, but I need each of them to be certain types of players. So that's why you sort of have to break it down into positions. And maybe I was just thinking maybe this will help. So here I have 18, and I want to choose 9 of them. Well, if you add up the top row here, that gives you, again, there's 18 total players. If you add up this row, that'll give you 9. So I'm still choosing 9 players out of these 18 players, but I want to do it in such a way that a certain number come from each group there. And it's like I need 1 pitcher, and I need 3 outfielders, and I need 5 infielders, which is why you're multiplying those all together. Yeah, Matt.
Is that always going to be the case when you multiply like the top, like you always have 18 and then the
Yep. So that'll always be the case. Yeah. Yep.
On the exam, how would you want us? Do you want us to come down to that final percentage?
Oh yeah. So if something like this showed up on the exam, you can just leave it like that. That's totally fine. Yeah. Yep. Leaving it in factorial or a combination, whatever notation, is totally fine. Okay. Next request. Anybody? No. Okay. Let's do number 5. That's somewhat arbitrarily selected here. Okay, so I have a certain make and model of a car is recalled because the airbags are bad, and 1% of the time they are the airbags fail. So that's not good. So suppose that 20 of these cars are randomly selected. And so first here I want to find the mean and standard deviation of the number of cars whose airbags fail in a head-on collision. So let's do some notation here. Let's let x equal the number of cars whose airbags fail. Again, of these 20. Okay, so what type of a random variable is x going to be? Binomial. So why is this a binomial random variable? Right. So I have either each car's airbags will either fail or not fail. That's good. Right. I have a set number of cars. I have 20 cars that I'm looking at. Yep. And then there's that sort of that caveat here. They're randomly selected. So again, for the binomial, you need to have independent observations or something like that. So randomly selected is sort of our code language for them all being independent. So we know here that x is distributed as a binomial random variable with n equals to 20 and success probability, or here failure probability, I guess, equal to 0.1. So we're talking about success probability in binomial. It's not always a good success is not always a good thing. Okay, so that's probably that's the bulk. Getting to this point is probably the bulk of this question. Is that okay? Everyone able to identify this as a binomial situation? Okay, so then what's the expected value of a binomial random variable? In general, it's what is it? Yeah, n times p, right? So this is equal to n times p, which here is 20 times 0.01, which gives me 0.2. So out of those 20 cars, I expect 0.2 of them to fail. Okay, so that's the mean. What about the standard deviation of x? Yes, so the standard deviation is the square root of the variance, right? So that's the square root of the variance of x. And then, Stephen, yes, you're exactly right. This is just n times p times 1 minus p. So square root of 20 times 0.01 times 0.99, which is 0.445. So you'd be going down the wrong. You could do it, but you'd be going down the wrong track to try to find the expected value and variance directly. You're welcome. I mean, that's why we talk about these properties. You can just use them. You can just say, I know what the mean and variance of a binomial is. There it is. Done. Moving on. Yeah, Kevin.
Is e of x squared like the component of the variance net and p binomial?
So what's the expected value of x squared? So we never talked about that.
Okay. All right.
Yeah, so you wouldn't, I wouldn't ask you to calculate that. But, I mean, you could use the identity that the variance equals that minus the expected value of x squared. You could sort of solve that backwards if you wanted to find that. But that's not something we've talked about. Yeah, Devin.
Just for the binomial distribution, is there one thing that'll tell us that it's the binomial, or do we have to look for several of them?
Yeah, so you mean how can I identify this problem as a binomial?
Yeah, like, can we just say that they're randomly selected and automatically assume that, or do we have to look for?
Oh, yeah. So if you can just jump and say this is x is binomial, 20 and 0.01, that's fine. You don't need to say. I mean, I could ask you to explain, like, why is this a binomial random variable? But if I don't ask you, then you don't need to say, here's how I know this is a binomial.
So, is there one thing that could tip us off, or are there
Yeah.
multiple things?
Well, so it's kind of what we just. So how do you know it's a binomial? It's kind of what we were just talking about. So for a binomial, you need two outcomes, either success or fail, or that can mean different things, right? So one of two outcomes. I need a fixed number of things. So here, like, I have 20 cars, so I have a certain number of cars, and then I need independence among those trials. So the randomly selected is the tip off there, but usually if you have a fixed number of things, that's sort of, I should start thinking about the binomial distribution.
Thank you.
Yeah.
Would you explain why the variance is equal to MP times 1 minus P?
Could I explain why the variance is equal to that? Yes. Well, so the variance of x by definition is the expected value of x minus the expected value of x squared. Right? So remember, running out of space here. I'm going to jump over here. Remember that the expected value, this is a good review. Remember the expected value of a function of x. You remember how to get there? Yeah, so that's just, for a discrete thing like this, we're just going to sum over all possible values of x times that function times the PMF of that value. So if x goes from 0 to 20, for example here, I can make the summation equals from 0 to 20. And then just calculate the h of x, whatever that is, times the probability of that value happening. So if I want to know the variance, that would be, so if h of x, so if that equals if that equals x minus the expected value of x squared, if that's my function of x, then I can just sum from x equals 0 to 20 of x minus the mean here, which is 0.2 squared, and then take that times the probability mass function of each value. So from there it gets messy. I'm not going to actually walk through that, how to actually calculate that thing, but that's how you would do it. And I would never ask you to do that on the exam. But that's a good reminder. Is this thing right here? So if I want the expected value of a function of x, that's you can calculate it that way, unless that function is like an ax plus b. If it's a linear thing, then we have certain rules for that, and you can just sort of jump straight to there. So that shows up somewhere on this review, but that's a good reminder to look at this point. Okay, let me clear myself some space here. Okay, so same setup here. X is still binomial with 20 number of cars. I have 20, and success probability is 0.01. So now part B here, what's the probability that at least 2 of the cars have airbags fail in a head-on collision? So this is the probability of what? Yeah, I want to know the probability that x is greater than or equal to 2. So again, remember here x was the number of cars whose airbags fail out of these 20, so that's just the probability that x is bigger than or equal to 2. And here you can use, from here, I guess you can kind of use your favorite way of solving these type of problems. I'm going to do the 1 minus way, but I was talking to someone earlier and I realized that I need to maybe make this a little bit more clear. So if I want to be exactly careful about this, this is the probability, 1 minus the probability that x is less than 2, right? So in our, more recently in chapter 4, I've been very casual and can put like a less than or equal to there, because with a continuous random variable, the endpoints don't really matter. But here in a discrete case, it does very much matter. So sort of formally, that's what this thing is. But what's the probability that x is less than 2? How could we rewrite that?
1 less than or equal to 1.
Right, yeah. So remember, the only possible values x can take on are 0, 1, 2, 3, 4. So the only cases that x is less than 2 is just when x is less than or equal to 1. That's a good reminder, just to be careful. In a discrete, for a discrete random variable like the binomial, you want to be careful. Your endpoints do matter here. Okay, so now if you want to use the table, you can use the table. If you want to, we could also do this directly. So this is 1 minus the probability that x equals 0 minus the probability that x equals 1, and we could calculate each one of those individually. So 1 minus 20, choose 0 times 0.01 to the 0 times 1 minus 0.01 to the 20th minus 20, choose 1. Again, I'm just writing out the binomial probability mass function here. So the 1 times 1 minus 0.01 to the 19th. I'm just writing out the binomial probability mass function here. But I did the trouble to get to this statement right here, so I could also use the CDF. I could also use the table to use the CDF via the table to figure out what this thing is. So if you go to the table tells you that this thing is equal to 0.983. It'll be a little faster than calculating each of those probabilities and adding them up. So again, remember the table, you want to go to find the right. So here we have n equals 20, so I'll go to the n equals 20 section of that table, find the right success probability column, so p equals 0.01, and then I would go down to where the 1 row and figure out what number that is. So this is 1 minus 0.983, or 0.017. Everybody okay with that? Okay. So a similar question: what's the probability that 16 of the cars have airbags that do not fail in a head-on collision? Sorry, 16. I believe this should say 16 or more. Don't know why that didn't show up on my notes here. Is that right, Devin? Is that what's on the? Okay, yeah. So what's the probability that 16 or more of the cars have airbags that do not fail in a head-on collision? Anybody have an idea of how to calculate this one?
Can't you just say that 4 of them do fail, and then do p the probability of x less than or equal to 4 minus the probability of x less than or equal to 3? Because you're just finding just equal to 4, right? Or just equal to 16 that do work.
Well, that's what the slide says, but we do want the or more in there.
Oh.
So the probability, let's just write this out. The probability that 16 or more, but then you were exactly right, Stephen. The probability that 16 or more do not fail how does that? So if 16 or more do fail,
And 4 or more don't. Or
then
4 or more do, because those do not fail. So.
okay, right.
Or
So
less.
we can think about how many. If 16 or more are going to fail, then how does that? How many of them?
Or less, yeah.
Right. So 4 or less do fail. So that's almost. So if
And we need more than that.
so that yeah. So then we can. I'm just noticing I have an error in my solutions. Okay, so the probability that 4 or less do fail, that's just the probability that x is less than or equal to 4, right? Maybe, yeah. So this is equal to 1 minus, well, never mind. We can look this up directly in the table and figure out what that number is. And I have written down the wrong number, so I won't fill that in. Does anybody have the table in front of them? Not worth it. So I accidentally wrote down the probability that x is less than or equal to 3, which was about 0.999. But so I have the wrong number there. I apologize. But this should be right. So it's just a good point that you can, when you're doing a binomial, you can either look at, doesn't matter which one you call a success or a failure, just keep your probabilities straight there. Okay. So now taking this one step further, so now suppose that we have 70 cars that are randomly selected, and now we want to use this Poisson approximation for the binomial probability that at least 2 cars have airbags that fail in a head-on collision. Then we need to just double check that it is indeed okay for us to use this approximation. So again, so ignoring this first part of the question, now if we let x be the number of cars that fail, this is binomial. What's the exact distribution here? So now if I have 70 cars, yeah. So now x is a binomial random variable, still binomial random variable. Now I have 70 cars, the same success probability there. But again, if I want to use the Poisson approximation, I need 2 things to be true. Does anybody remember what those are off the top of your head?
N is greater than 50, and U is less than 2.
N times P is less than 5.
That's exactly right. Yeah. So that tells us what the what mu is going to be. Yeah. So I need my sample size to be bigger than 50. So here I have 70 cars, which is bigger than 50, and I also need n times p to be bigger than, less than 5. So here n times p is 70 times 0.01, which is 0.7. Which most days anyway is less than 5. So since both of these things check out, we are okay to use the approximation. Okay, so the approximation is, so if x, the exact distribution here is that x is binomial, the approximate distribution is that x is approximately distributed as a Poisson, and then what's the parameter in my Poisson based on n and p? Yeah, n times p, right? So n times p, which is Poisson 0.7. Okay, so the probability that I want is the probability that x. So I want the probability that at least 2 cars have airbags that fail in a head-on collision. That's the probability that x is bigger than or equal to 2. So we can approximate that with a Poisson probability of being less than or equal to 2. So here, this is a binomial. It's approximately equal to the probability that x is greater than or equal to 2 when I have a Poisson here. So again, same trick. This is 1 minus the probability that x is less than or equal to 1. And my Poisson probability here is, again, remember it's e to the negative mu times mu to the x over x factorial. So e to the negative 0.7 times 0.7 to the x here, which is, well, I guess I need to add up some probabilities here. Divided by 1 factorial. And then I also need to do that same thing for 0. So e to the negative 0.7 times 0.7 to the 0 divided by 0 factorial. That would be the way to calculate those things by hand. Or, again, I can use the table because I have a probability of being less than or equal to something. So the table is probably a little faster way to do that. And if you look up in the correct row and column, that will be a 1 minus 0.844, which gives us the probability here of 0.156. Yes, Andrew?
What is 0 factorial?
What is 0 factorial, anybody? 1. Yeah, so that's 0 factorial is 1. That's, yeah, so it's like there's exactly one way to choose 0 things out of 0 things. It's kind of a little mathematical identity. Yeah.
For the other part, where there was the 16 or whatever that he was putting,
Mm-hmm.
could you do it like, if you did x as binomial and you did 20 and then 0.99?
Absolutely, yes, absolutely. So let's.
Before I did it in my calculator, I tried to do it backwards and I would get different numbers.
Okay.
Like, I don't know how.
So you should be able to do that the same way. So if let's instead let y equal the number of 20 that do not fail. Then yeah, like you said, y is binomial 20, and again the success probability now is not, their airbag's not failing, so that has probability 0.99. And so yeah, I want the probability that y is bigger than or equal to 16. So again, the solution was wrong, if that's tripping you up. The posted solution was wrong, but this should give you the.
Because I tried it on reverse like a while ago. I didn't even try to see it.
Okay. So yeah, so what's 1 minus the probability that y is less than or equal to 15? Well, again, you could calculate it out that way as well. That will give you the same answer. Yeah.
You know how to do a binomial on your calculator, like what parameters you need to type?
Oh yeah, so the binomial CDF, or which one are you talking about?
Is it different for like the binomial PDF and CDF?
Actually, no. So the order you want to put in, you want to put n, p, and then x. So I guess I could calculate this thing here. 20.
So I got 0.999.
Yeah, so this is going to be 1 minus 0.00001 or something like that. So it's going to be almost 1.
So your answer was right then?
Yeah. Well, again, it's
Or
off by. It's the wrong. I have x less than or equal to 3 instead of less than or equal to 4, but within rounding error, it's about the same.
So we had 4.
Yeah, let's double check that one. Yeah, so it's like 0.9999986 something there. Yeah. So yeah, if you're using your calculator, you put in n, then p, then x. Okay. Anybody have another problem they would like to look at? Has anybody gained a request in the last 20 minutes? No? Okay, well let's try number 8. That was a little tricky. Okay, so here during a particular soccer season, the Rutgers men's team had the highest average number of yellow cards per game, or 2, in the Big East. And suppose we take a particular soccer game from that season. So what is the probability of having at least 2 yellow cards during the game? Anybody have a idea of a strategy here, or? Yeah.
We just assume this is a Poisson distribution because there's no fixed number of trials in there, doesn't tell us.
Yep, exactly right. So, yeah, so it doesn't say, it doesn't tell me what I need for the Poisson to be true. It doesn't tell me that I have a Poisson distribution, but again, that's, thinking about I'm counting something. I'm counting the number of yellow cards here, and I have no upper, like there's no sort of upper limit there. So yeah, Poisson is exactly the way to go. So maybe sort of a general, let's go back to red. I'll go back to x. If I let x equal the number of yellow cards during the game. Well, I guess another way to pick this out as Poisson is you have a fixed amount of time, right? So I don't know how many possible yellow cards I could get. I could get any number theoretically, but it's a fixed amount of time. So I'm counting something within a fixed unit of time. So that's another tip off. Yeah. So x is Poisson, and then what's my parameter here? It's just the mean, right? So 2. So again, that's kind of the hardest part of this question, is identifying what random variable we're working with here. Is everybody on board? Is everyone? Now that I've told you, maybe it's hard to not see it, but so again, we kind of for this exam anyway, we're not into like the normal distribution and all these things yet. So really, your 2 choices are binomial and Poisson, right? So binomial, we talked about, you have a fixed number of objects or subjects or something like that, and you're looking at a success or failure for each one of those. Poisson is your counting, but you don't know how many, like there's no upper limit on that thing, but you have sort of a fixed window of time or a fixed unit of measure or something like that. That's kind of your tip-off for the Poisson. Okay, so I want the probability that I have at least 2 yellow cards. So that's the probability that x is what? Greater than or equal to 2. Got a lot of 2's in here. So again, this is 1 minus the probability that x is less than or equal to 1. And I would recommend going to the table. So if you go to the table and go to the column where mu equals to 2 and find the 1 row, this is 1 minus 0.406 or 0.594. Sorry I'm skipping over that step, but again, to get from here to here, I use the table. Yeah. Absolutely, yeah. I will give you whatever tables you need. You will be given. Yep. So if you can use your calculator, that's great. Not everyone has a calculator. That's fine. The table is your backup plan there. Yeah. Okay. What is the variance of the number of yellow cards that happened during the game? So I want the variance of x, which is the number of yellow cards. What's the variance of a Poisson? Yeah, same as the mean, right? So the mean of the Poisson distribution is the same as the variance here. The mean is what? 2. So the variance is also 2. Okay? So practice what we were referencing earlier. So suppose at the next practice the coach makes the team run 25 sprints for every yellow card received during the game. What are the expected value and variance of the number of sprints the team has to run? Anybody have a strategy to try here?
Can we use the property about the linear function of x for expected value?
Absolutely, yeah. So if we want to know something about the expected number and variance of the number of sprints, yeah, you want to express that's a function of how many yellow cards they get, right? So, so let's let the number of sprints is equal to some function, let's say h of x, which is the number of yellow cards they get, right? And so how many sprints do they have to do as in terms of x? Yeah, 25x. So for every yellow card they get, I have to do 25 sprints. Okay, so again, if I want to know the expected number of sprints, well, that's just the expected value of h of x. So I could, again, there's a formal definition for what that means, but again, we have, since h is a linear function, we have some special properties. So this is expected value of 25x. That's what h of x is. What can I do with that? Yeah, Matt.
You can multiply, or you can take the 25 out and pop it out front.
Exactly right.
The value of x by 25.
So I can pull the 25 outside the expectation there and do it this way. And so again, the expected value of x is just 2. So it's been a long day, right? So 25 times 2 is 50 there. Okay, so similarly, the variance of the number of sprints, well, that's just the variance of h of x. It's the variance of 25 times x. So what's my rule for the variance if I have a linear function? Exactly right. So I can pull that 25 outside of the variance, but now I got to square it. Yeah. So this is equal to 25 squared times the variance of x, which is 25. You guys all remember your multiplication, your squares tables there, right? 625 times the variance is 2, or 1250. Yeah.
Why did you square the 25 when you took it out?
So why did I square the 25 when I brought it outside? That is, well, that's a property of the variance. So that's always true. So the variance of a times x is always equal to a squared times the variance of x. I think we actually figured out how to kind of prove that in class, but again, that's something you can just use.
So if b was added to variance of x plus b, would you square b if you pulled it out or no?
Yeah, so what if I had, let's go back here, I have one more space here. So what about the variance of a of ax plus b? Yeah, almost, yeah. So adding on a b doesn't change the variance. So yeah, so this again was something I think maybe in that same, this is still equal to a squared times the variance of x. So adding on a constant doesn't change the variance. Again, you can think about kind of what I said earlier was the variance is a measure of how spread out something is. So if I just add something to that, I'm not changing how spread out it is. So I'm just kind of like I'm also picking up the distribution and shifting it around, but I'm not making it more or less spread out there. So adding on a b doesn't change the variance. Yeah, Kevin.
You have variance of x plus bx. You just evaluate those variance of x plus variance of bx.
Ah, great question. So if I had the variance of x plus bx, is that what you said?
Yeah.
So well, here's your out here. You could take variance of 1 plus b times x, and do it that way. So now you have 1 plus b squared times the variance of x. In general, if I have like the variance of x plus some other random variable, that's something we'll talk about in chapter 5. So that's kind of looking at a variance of more than one random variable. So no need to worry about that for now. But if you had, well, let's say you had like the variance of, I don't know, x plus x squared or something like that.
Yeah.
So that is not equal to the variance of x plus the variance of x squared. That is not true. Not, well, yeah, not in general anyway. Okay, so I guess the point is that here you wouldn't want to go about calculating a new expected value because that's a lot of work. But in a simpler example, if you want to find like that homework problem that was about the expected charge of that book, I think that was that number 7 on the homework you turned in today. You could use these same tricks. You could calculate it out again directly using the identity of so the expected value of h of x, wrote this up earlier, that would be equal to the sum over all x times that function of x times the PMF of evaluated at x. So you could calculate it out directly again, or you could just use those properties that we just talked about. That's definitely the faster way of doing that. It's kind of we'll give you the same result. Either way is fine. But that's going to be a short. If h of x is a linear function, then that makes your life a lot easier there. Okay. Oh, one more. I guess we have one more part of this question to go still. So again, now we're supposing that this number of yellow cards per game is a Poisson process. What's the probability of having exactly one yellow card in the first half of the game only? Okay, so let's let y equal the number of yellow cards in the first half. What kind of distribution is y going to have? So before we know that the number of yellow cards in the whole game is Poisson with mean 2, what if I'm just looking at the first half of the game? So ignoring the parameter, what kind of a distribution is y going to have? The number of yellow cards. I'm counting a number of occurrences in a fixed amount of time. Yeah, so it's going to have. So that's where we're going. But it's going to have a Poisson distribution still. So that's still the same. So y is still Poisson. And if you think back to your Poisson process notes, again that kind of makes sense. So I'm still counting the number of things in some fixed amount of time. So I still have a Poisson distribution, but the mean is going to change, right? So the average number of occurrences per full game was 2. But then now I'm only considering half of the game. So the amount of time t that I have there is a half. So this is the mu times t type of a situation. So mu is still 2, but the amount of time I'm only looking at half of a game instead of one game. So it's Poisson with parameter 1 there. And then the probability that I have exactly one yellow card, that's probably that y equals 1. Which again, I can use the table, or I can just calculate the PMF is e to the negative mu times t, which is e to the negative 1 times 1 to the 1 divided by 1 factorial. Which is just e to the negative 1, or 0.3679. So if I ask you what the number of, so if instead y was the number of yellow cards in 3 games, what distribution would that have? It'd still be Poisson, right? And then what's my mean? 6, right? So I want 3 games, so I have 2 per game. So I would expect there to be 6 total yellow cards in those 3 games. So again, the difference between the Poisson random variable and the Poisson process is the Poisson process you can talk about for different lengths of time or different lengths of or different units of measure. Okay. Maybe pick out one more to do. Anybody still no preferences? You guys are forcing my hand here. 7, yeah, absolutely. Where is number 7? Ah, excellent. Yep. Okay, it's number 7. Do something a little different here. That's good. Okay, so now we have a random variable whose probability density function is given by this nice little thing here. So since we have a probability density function, we have a continuous random variable. So we want to know the expected value of x here. So it's time to do some calculus, right? So in general, the expected value of x for a continuous random variable is, we do an integral over the entire real line, negative infinity to positive infinity, of x times the PDF, f times f of x dx. So that's just by definition. There's nothing about the example that I've written up there yet. I realized I made this jump before. So how can I rewrite this integral and y? So how can I change my endpoints here? 0 to infinity? Yeah. So I only need to do this integral over ranges of values of x that I have where the PDF is positive, right? So for example. If I consider negative infinity to 1, well, the PDF is 0 in that range, and so that doesn't contribute anything to my integral there. So I can rewrite this thing as integral from 1 to infinity because that's the range in which the PDF is positive. It's bigger than 0 in that range. Everybody okay? Why we switch the endpoints there? Okay, so this is just 1 to infinity of x times alpha divided by x to the alpha plus 1 dx. So can put the x's together. This is alpha over x to the alpha dx. So the one of the x in the numerator cancels out one of the x's in the denominator. And so this is just alpha times the integral of x to the negative alpha. So alpha is bigger than 1. What's that integral? Integral of x to the negative alpha. Integral of x to any power is what? You add 1 to the power and divide by the new power. Yeah. So this is x to the negative alpha. Add 1 to it and divide by the new power, negative alpha plus 1. Then I want to evaluate that at 1 and infinity. So you guys don't need to see me do algebra here. This is going to be equal to alpha over alpha minus 1. So because I have a negative power of x and alpha is bigger than 1, that when I put in infinity, that gives me a 0. And then I just have that other situation. Yeah. So I'll let you fill in the details there. Out of interest of time, we'll press on. Is that okay with everybody? Skipping some details there again, but okay. It's the expected value. So what is the cumulative distribution function, CDF of x? So I have the PDF. How do I get this the CDF from the PDF? Integral, exactly right. So the CDF is just the integral from, again, negative infinity up to x of the PDF. So f of y dy. So let's think about just for x bigger than 1 for now. This is just 1 up to x of alpha over y to the alpha plus 1. Can rewrite this 1 up to x of, let's put the alpha out front, times y to the negative alpha plus 1 integral is going to be very, very similar to what we saw before. This is going to be y to the negative alpha divided by alpha, evaluated at 1 and x. And again, I'll skip over some details there out of interest of time. 1 minus x to the negative alpha. Again, leaving out more steps, but there we go. Everyone following me here? We on the same page? Okay, so now let's set alpha equal to 4 and let's find the probability that x is between 2 and 3. So again, I want the probability that x is between 2 and 3, so x is bigger than or equal to 2, less than or equal to 3. Maybe just to check here, does anybody have a problem if I just write that? Are those two things the same? They different? They're the same. So these you could calculate either one of these things would be the same, and why is that? Yeah. So here I have a continuous random variable, so the endpoints are not going to change the answer. The probability of a single value, remember, is always 0 for a continuous. Very good. So this is, put this in terms of the CDF. This is the probability that x is less than or equal to 3 minus the probability that x is less than or equal to 2. Again, that's the CDF. So the CDF at 3 minus CDF at 2. And now with alpha equal to 4, I can use that what we just found on the previous slide. So this is 1 minus x to the negative alpha, so negative 4 minus 1 minus 2, rather. 2 to the negative 4. So I'm just, again, I'm plugging in alpha equals to 4 into that, what we found in part B. And this is 2 to the negative 4 minus 3 to the negative 4, or about 0.05015. So remember the CDF was 1 minus x to the negative alpha. right. Maybe in lieu of starting a brand new problem, maybe I'll stop the recording. Or does anyone have any final questions on any review of these practice problems? Yeah.
I was just a question about the exam. So what kind of
Okay. Hold on that thought 1 second. So we're okay on these exam review activities for now? Okay.